In Linda's lab, her colleagues regularly use vacuum pumps for a variety of benchtop tasks, to provide suction for aspiration and filtration, and to control vapor pressure for solvent evaporation in concentrators, gel dryers, vacuum ovens, desiccators, and rotary evaporators. Linda's lab has been using the same pump for quite some time. It's a standard oil-sealed rotary vane pump, the kind you might find in a number of labs. And like a lot of older pumps, Linda's pump is very loud, requires regular oil changes, and costly disposal of potentially contaminated waste oil. How's that old pump working for you, Linda? It's time for Linda to buy a new vacuum solution for her lab. Some applications require extremely deep vacuum. Atomic physics, field emission microscopy, and X-ray photoelectric spectroscopy may require vacuum pressures between 10 to the minus 3 to 10 to the minus 9 millibars. For these applications, a diffusion pump, ion pump, or turbomolecular pump may be the best or only choice. Vacuum can also be used to improve instrument sensitivity in applications like mass spectrometry. However, these systems are usually integrated with the instrument and are seldom purchased separately. A great number of applications use standard vacuum pressures in the range from roughly 200 millibars to 10 to the minus 3 millibar. Rotary vane, dry scroll, and diaphragm pumps all provide vacuum pressures in this range. Linda needs a vacuum pump suitable for evaporation of solvents, and knows that when purchasing a new pump for her lab, there are a number of considerations. If evaporation is your goal, you'll need to know what types of solvents you plan to work with. Solvents with low boiling points like acetone or methylene chloride require less vacuum to evaporate than solvents like benzene or acetonitrile. For solvents with high boiling points like water or toluene, you're going to need a deeper end vacuum to remove the solvents effectively. And remember, if you're working with corrosive solvents, make sure your pump has a corrosion-resistant flow path. This will protect the pump from corrosive vapors and avoid the need for inconvenient cold traps. When it comes to vacuum pumps, bigger isn't always better. A pump that is too big or has too high a flow capacity can be hard to control, will be inefficient, and have a higher operating cost. On the other hand, a pump that is too small or has too low a flow rate will result in slow evaporation and long processing times. There are a few options available for vacuum control. Manual control is the simplest method and involves the use of a stopcock or manual valve to adjust vacuum. Unfortunately, you'll have to monitor the vacuum closely, as vacuum requirements may change. Two-point control allows you to cycle between a high and low set point, which will allow you to leave the process unattended once the settings are determined. However, for best results you may want to consider a pump with adaptive vacuum control. This is the most accurate method, as the control precisely matches the speed of the pump with the requirements of the process. For Linda's lab, the best system is going to be a diaphragm pump. These pumps are affordable, versatile, and oil-free, meaning no more inconvenient oil changes or expensive disposal costs. And with a corrosion-free flow path, this pump will be both long-lasting and low maintenance. And with low noise operation, Linda finally will have some peace and quiet in her lab. Lab Manager. When we talk science, we mean business. Brought to you by Knf Neuberger Inc., quality pumps and laboratory equipment.